All right, in today's lesson, we're going to be talking about vertical and horizontal asymptotes. Recall that asymptotes are helper lines. They're not actually parts of the function, but they are lines that we can use that help us graph them. The graph often gets very, very, very close to these lines, but never touches them, and there is an exception to that I'll get to later. And they are always drawn with dotted lines because they are not actually a part of your graph. They are just guidelines. The first type of asymptotes we're going to be talking about are vertical asymptotes. Vertical asymptotes are written as x equals to a number. And essentially what happens is that at a vertical asymptote, the y values of your function are either shooting off to negative infinity, so down, or positive infinity, up. There's a couple of different ways that this might look. If this is your vertical asymptote, for example, if they both shoot off to positive infinity, then my function would look like this. And then of course it's doing something on the other side. Another option is that if this is my vertical asymptote, they're both going down to negative infinity, that way. Or perhaps you've got a split where one of them is going up and the other one is going down. To determine the location of our vertical asymptotes, we need to set every factor in the denominator equal to 0 and then solve. That's what we're looking for here. Okay, and so first we need to make sure our denominator is indeed factored so that we can do that. Let's look at a couple of examples here. So in our first example, I'm given the function f of x is equal to x minus 1 divided by x squared minus x minus 12. I need to factor my denominator. So I'm looking for two numbers that add to negative 1 and multiply to negative 12. Negative 4 and positive 3 are the numbers that I want. And so I'm going to set both of these not equal to 0. Our function cannot equal them. So I'm going to do x minus 4 cannot equal to 0, just like x plus 3 cannot equal to 0. And I'm going to solve. This cannot equal to is like the same thing as an equal sign. I'm going to rearrange. We know that x cannot be equal to 4, and it cannot be equal to negative 3. So I have vertical asymptotes, and I'm going to write those as VAs at x is equal to negative 3 and 4. There's two vertical asymptotes here. Okay, another quick example, the function f of x is equal to x plus 3 divided by 2x squared plus 5x minus 5. Once again, I need to factor my denominator. This one is complex trinomial, so I'm going to take a little bit longer to do it. I need two numbers that add to 5 and multiply to negative 10. Nope. Sorry, typo in the question. This shouldn't be 5. This should be 25. There we go. Okay, two numbers that add to 5 and multiply to negative 50, in this case, are positive 10 and negative 5. So I'm going to decompose my denominator. And then factor by grouping. And then finish off my factoring by grouping. Okay, I set each factor not equal to 0. So 2x minus 5 cannot be equal to 0. And x plus 5 cannot be equal to 0. I'm going to rearrange, so I have x cannot be 5 over 2, and x cannot be negative 5. And so therefore I've got BAs at x is -5 and at 5/2. So it's pretty straightforward how to find the location of your vertical asymptotes, and then from here we could graph them on our function. But the other step is we actually need to figure out how our function is going to be behaving as it approaches the vertical asymptote. So that's the next problem here. How do we figure that out? Okay, let's do one example slowly here. Determine the vertical asymptote and how the function behaves at each for this function. So the very first thing we need to do is we need to determine the location of them. And just like we did previously, I'm going to start by factoring my denominator. I need two numbers that add to -1 and multiply to -2. Those two numbers are -2 and +1. I set each of them not equal to 0. And I locate my vertical asymptotes at -1 and +2. Now what we need to do is we're going to pick a test value on either side of each vertical asymptote, and then we're going to test what the function is doing. We're going to see, okay? So let's start with our first vertical asymptote here at x is equal to -1. A number that is a little bit more negative, a little bit to the left, would be test at, for example, -1.1. Okay, this is going to be our left test value. I'm going to substitute this into the function. F of -1.1 divided by, and I'm going to use the factored form in my denominator because it's a little bit easier. Okay, I'm not going to show all of my work here. I'm just going to type this into my calculator. -1.1 squared is 1.21. And then I have to add 4 times -1.1 plus 3. I get a numerator of -0.19. My denominator, I've got -1.1 minus 2 times -1.1 plus 1, 0.31. And let's do that division. -0.19 divided by 0.31 is equal to, and I'm just going to round it, -0.61. This is a negative number, okay? Which means that we are going down to the negatives. We're going to -infinity, okay? We're going to do the same thing. We're going to test on the right. And so I need a number that's a little bit to the right of -1. And I'm going to test -0.9. I'm going to follow the exact same process. And in the interest of time, I'm just going to tell you that my function at -0.9 is -0.72. So this is also shooting down negative. It's going towards -infinity at x is equal to -0.9, or coming from the right. Okay, we're going to repeat this now for our second vertical asymptote. We need to test again for 2. Okay, I'm going to do this over here. For x is equal to +2, I'm going to test a little bit to the left, so I'm going to test at 1.9, and I'm also going to test at 2.1. I'll write x equals 2.1. Ooh. Okay, and once again, in the interest of time, I'm just going to jump straight to the answer here. My function at 1.9 is negative 49, and my function at 2.1 is positive 51. So at 1.9, my function is going negative once again. It's going to negative infinity. But at 2.1, it's positive. So I'm going towards positive infinity. What I'm going to do here is I'm going to now summarize my findings, okay? So the way this is going to look, remember we had two factors that we were working with. There are two vertical asymptotes, okay? I'm going to say here, let's start with the negative 1. As x approaches negative 1 from the left, that little negative sign up top here, this means from the left. So as x approaches negative 1 from the left, and which one was that? It was hitting down to negative infinity, so I'm going to write y approaches negative infinity. We also tested from the right. As x approaches negative 1 from the right, the little plus sign means from the right. Y approaches, and we tested here, negative 0.9 got me a negative number again, so y went down to negative infinity. Okay, I'm going to do it for my other vertical asymptote now, which was 2. As x approaches 2 from the left, y went to negative infinity. On the left-hand side, it went to negative infinity. As x approached 2 from the right-hand side, and here's where we tested the value 2.1, it went positive. We went to positive infinity. And so what does this look like for our sketch? Because of course, ultimately, we are looking at sketching our function here. Just really roughly, if I were to draw a Cartesian grid, and we added our two vertical asymptotes, so we had one at negative 1, and we had another one at positive 2. I know my scale is off, but that's okay. Here's what I would do is I would add these little arrows. So for negative 1, it went down to negative infinity on both sides. So I would add a little arrow down to negative infinity on both sides. For my 2 vertical asymptote, it went down to negative infinity on the left, but it went up to positive infinity on the right. And so eventually we'll be in a place where we're able to have a little bit more in between, right? We're going to know what's happening in this section. We're going to know what's happening in this section and over here. But this is the first piece of the puzzle, is to determine your vertical asymptote location. Okay, let's do another example. Determine the vertical asymptotes and how the function behaves at each for this function. F of x is equal to x plus 4 over 6x squared minus 7x minus 20. Okay, we need to first determine where they are, which means we need to factor the denominator. I'm looking for two numbers that are going to add to negative 7 and multiply to negative 120. And those numbers are going to be negative 15, positive 8. So I'm going to decompose 6x squared minus 15x plus 8x minus 20. And now factor by grouping. I can factor out a 3x, leaving me with 2x minus 5. And I can also factor out a 4, leaving me with, once again, 2x minus 5. I'll finish my factor by grouping by combining my two groups. Awesome. So I've located, or I've factored my denominator. Now I can go ahead and I can find the location of my x-intercepts, or my vertical asymptotes, I should say. I'm going to set each factor not equal to 0. And then rearrange to solve. So our two vertical asymptotes in this case are located at negative 4 over 3 and positive 5 over 2. Okay, now we need to figure out the behavior of our function at each of these. For reference, negative 4 over 3 is about negative 1.33. And 5 over 2 is equal to 2.5. Okay, so let's test for our x-intercept, or for our vertical asymptote, I should say, negative 4 over 3. We'll test from the left, so we'll pick a number that's slightly more negative than 1.33, and I'll try negative 1.4. And substitute this in. And then go ahead and solve. Actually, I'm just going to skip that one. We can see here that it's going to be positive at the end of the day. I've got a positive numerator and then a double negative in my denominator. We'll do the math, but we know it's going to be positive. This is about 1.67, so it's positive. Yay. Okay, and then we'll test again here for a number that is slightly more positive. So we'll test negative 1.2. We want to be picking numbers that are really close to our vertical asymptote. So I know thinking about like rational, polynomial functions, and we could just pick numbers like on any interval, and we just picked ones that were convenient. You want to pick numbers here that are quite close to your asymptote so that you're getting accurate results. So as much as like picking negative 1 would be a lot easier, or even picking 0 would be easier, you want to stay close to that asymptote. Okay, my numerator here will be 2.8. And then I'll have a 0.4 times negative 7.4. So this is going to be a negative number because we've only got one negative at the end of the day. So we'll go 2.8 divided by 0.4 times negative 7.4, which is, I got negative 0.95. And so this is negative at the end of the day. It's going negative. All right, this is just our first asymptote, so now we need to check the other. And our second asymptote was at 5 over 2. And we're going to do the exact same thing. 5 over 2 is 2.5, so to the left of that would be like 2.4. 2.4 plus 4 is going to be 6.4. And then I have 11.2 in my first bracket. And negative 0.2 in my second bracket. I'll do that division, but I think we can clearly see that it's going to be negative. This is about negative 2.9, so this one goes negative. And then we'll try on the last side, we'll test at a little bit to the right of 2.5 is like 2.6. So we'll do 2.6 plus 4, all divided by 3 times 2.6 plus 4. 2 times 2.6 minus 5. That's going to be 6.6. 3 times 2.6 plus 4 is 11.8. 2 times 2.6 minus 5 is 0.2. This will end up being positive. We will just finish off with the division though. This is about 2.8, so this guy goes positive. Okay, let's conclude here, and I'm just going to shift this up so I've got some more space. Okay, so we have, as x approaches negative 4/3 from the left, y goes to positive infinity. Got that here. As x approaches negative 4/3 to the right, y approaches negative infinity, which we got right there. Then we had, as x approaches 5/2 from the left, y approaches negative infinity. And as x approaches 5/2 from the right, y goes to positive infinity. Okay. We have now all of our end behavior, and if we wanted, we could draw a quick sketch. I'll just draw it down here. We'll have one asymptote over here. This will be at negative 4/3, and then our other asymptote here, 5/2. As x approaches negative 4/3 from the left, we go to positive infinity. From the right, we go to negative infinity. As x approaches 5/2 from the left, we go to negative infinity. And from the right, we go to positive infinity. So I think we can pretty clearly see that's the style of function we're dealing with here. There might be something in the middle here, but you can see overall it's going to be a degree 2. It's going to end up sort of rebounding along the way there. Okay, so that's it. That's everything you need to know about your vertical asymptotes. Now let's talk horizontal asymptotes. So horizontal asymptotes are written as y equals a number, and they're very similar to end behaviors when thinking about our polynomial functions, because we want to know essentially what's happening as things are getting really, really, really big, like as x is getting really, really, really big. The cool thing about these is you can cross them. Vertical asymptotes you can't. You can only get really close. Horizontal asymptotes you absolutely can cross. We use them because they're helpful for drawing. Okay, let's take a look for a sec at this function here. F of x is equal to 2x plus 8 divided by 5x minus 2. And we're just going to do a quick investigation here. By substituting in these three values into our function and seeing what happens. So as for f is equal to, or for x is equal to 1, I have 2 times 1 plus 8, all divided by 5 times 1 minus 2. which is 10 over 3. Or if we wanted about 3.33. Okay, what about for 10,000? F of 10,000 will be 2 times 10,000 plus 8, all divided by 5 times 10,000 minus 2, which will be what? 20,008 divided by 49,998. And if we actually do that math and put it as a decimal, that's about 0.4-ish. What about a million? If we try a million, F of 1 million. Do the same thing. 2 times 1 million plus 8. 5 times 1 million minus 2. Well, that's going to be 2,000,008 divided by 499,998. There's another 9 in the middle there. You do this division, it's actually also about 0.4. Which term is having the most impact on the answers here, particularly with the bottom two? Is it the 8 and the 2? They're not really doing anything here. Once the numbers get really big, they are not contributing very much, right? The numbers that are having the biggest impact are our first two terms in both of these cases. And what do these two terms have in common? They both have an x. And so which term matters the most? It's the term with the highest degree of x, right? The 8 and the 2 have a degree of 0. The 2 and the 5 have a degree of 1. Now let's just look for a second, really curiously, back at our initial question here. What if we divided 2 over 5? Interestingly, 2 over 5 is 0.4 exactly. Huh. 0.4? 0.4, not a coincidence. What we've just done is called taking the limit as x approaches infinity. And the way we write it is limit, or LIM, and then underneath you write x approaches infinity. So as x gets really, really, really big, okay, what's happening here? And we only really need to pay attention to the terms with the highest degree. Let's see what this looks like in action here, okay? We need to determine the value of the following limit. The limit as x approaches infinity of 2x minus 3 divided by x plus 1. Okay, we're being asked to find as x gets really big, or as x goes really far right. That's what the question is asking us. How does it look like on the end? The way that we do this properly, okay, we're going to take our original function and we need to divide every term by the highest degree of x. So in this case, the highest degree of x is x. I'm going to divide every single term. 2x divided by x, 3 divided by x divided by x, 1 divided by x. I can simplify. 2x divided by x is just 2. X divided by x is 1. Now what's going to happen to the fractions as x gets really, really, really large? Well, the denominator is going to get huge, right? And 3 is not going to be able to do much against that. So the denominator is going to get huge and it's going to become negligible. They are going to get very small. very, very close to 0, okay? Which means that we can sort of ignore them, okay? They are negligible. And so we can conclude by writing our limit at this point in time. We can sort of ignore the 3 over x and the 1 over x. Our limit here, as x approaches infinity, is just 2 over 1, which is 2. And this is what we use in order to find our horizontal asymptotes. Okay, we're checking these limits here. Okay, we're going to be using them to determine how our function looks as x gets really, really, really big to positive infinity and also down to negative infinity. And just like with vertical asymptotes, we need to know if the function is going to approach our horizontal asymptote either from above or from below. Okay, so we're going to do an example here. Determine the equation of the horizontal asymptote for the function f of x equals to 3x plus 5 divided by 2x minus 1, and also whether the graph approaches the asymptote from above or below. So first we need to figure out where the horizontal asymptote is, and we're going to do this by taking the limit. I need to take the limit as x approaches infinity of my function. 3x plus 5 over 2x minus 1. I divide every term by x. I'm going to simplify. And we know that those last two terms aren't going to be contributing much, so I can just ignore them. And so in this case, the limit, I'm just going to write it down here, is 3 over 2. This is where our horizontal asymptote is. Our horizontal asymptote is located at y equals 3 over 2. 3 over 2 is 1.5. And I'm using the decimals because we're working in decimals for the remainder of this question. So in order to figure out how our function behaves as it gets close to them, is we need to pick large x values in both the positive and negative directions, and then we're going to use them to test how the function behaves as it gets large. Okay, in the last page I used 10,000 and I used a million. That is overkill. You do not need to test values that are that big. I'm going to be using 100 and negative 100. Okay, so I'm going to test at x is equal to 100. What is my function at 100? 3 times 100 plus 5 divided by 2 times 100 minus 1. So that'll be 305 and 199. 305 divided by 199 is about 1.53. And this is above my horizontal asymptote, right? 1.53 is greater than. This is above the horizontal asymptote. So my function is approaching from above. Now we'll test again. Test at x is equal to negative 100. Okay, we put that in. F of negative 100 will go 3 times negative 100 plus 5 divided by 2 times negative 100 minus 1. So that's negative 300 plus 5, which is negative 295. And then negative 201. I type this into my calculator, I get about 1.47. And 1.47 is below my horizontal asymptote because it's less than. So we're going to summarize our findings here. We're going to finish things off. First off, we're going to say, well, as x approaches positive infinity, y approaches my horizontal asymptote, which was 3 over 2. And in this case, it's coming from above, so I write the little plus sign. It's coming from above. As x approaches negative infinity, y approaches my horizontal asymptote from below. Okay, so we can use this to sketch what it's actually going to look like in terms of a horizontal asymptote. So if we were to have our function here, our horizontal asymptote was at about 1.5, or exactly 1.5. On the right-hand side, I'm coming down from above. So I'd have an arrow going that way. And on the left-hand side, I'm coming from below. So I would have an arrow this way. Okay? We would then combine this with our vertical asymptotes and the end behavior at the vertical asymptotes to get an idea of how our function is behaving as it approaches all of the different asymptotes. Okay? The last thing before I let you go here. Horizontal asymptotes do not exist when the degree of the numerator is greater than the degree of the denominator. Okay? Let's look at a brief example here. We need to find the limit as x approaches infinity of this function, 2x squared minus 5x minus 3, all divided by x minus 3. Okay, so I'm going to do it. I'm going to divide all my terms by the highest degree of x. I'm going to simplify where I can. I have a 2, and then 5 over x, and then 3 over x squared, divided by, this will be 1 over x minus 3 over x squared. For all of these terms, they're going to go to 0, right? Because my denominator is going to get really, really, really big. And so my answer here is going to be 2 over 0. Which is impossible. And so when this happens, we get the famous line from Mean Girls, the limit does not exist. And we write D and E when that is the case. Okay? Really quick to see, you don't actually need to do this math to prove that the limit does not exist. You can just see directly from the question, because the degree of the numerator is higher than the degree of the denominator, the limit does not exist. Okay? I know that was a lot of information all in one. Take some time to digest, do some practice. You got this.